Hello and welcome back to another video. In this one, we're going to take a look at a small but practical application that is written in terms of our general purpose code base. So this is something that maybe a lot of people haven't seen, which is a fairly modern C++ application that is not based on the standard template libraries, which almost everything is. So you might find it interesting for that purpose. The general scenario here is that we're going to write a little server, which normally would run in the background as a service or something, but in this case, just a console application. And it will wait for a connection from a number of smart, quote unquote, smart sensors, which are just little test applications in this case for us to use for testing. Each of those sensors will report like 5 sensor values, internal and external humidity, internal, external temp, and luminosity, which are fairly common things for a multi-sensor to report. The server will just receive those messages, and it will collect the low and high values for each of them. And at the end, when we shut it down, it will show those values. So a fairly typical sort of socket-based server application. It uses JSON for the message format. So I'll just start this guy up here. It doesn't take any parameters. It's just using a hard-coded port 9999. So it's waiting for clients. And here I'll run one of the clients here, and I give it a sensor name. So it represents a particular sensor. So I'll call this one kitchen. So we can see we got a connection here, and I can do things like set external humidity, say 80. And if we look up here, we see we got a message from this guy. Set it to 60. Set internal humidity. Oops, I can't see the keyboard when I'm doing this. To 70. All right, so basically it's just collecting information. So if we just hit Control-C to kill it, it'll output the information that it got. For the ones that it never received any information, it just puts out question marks. So that's basically the application that we're going to demonstrate here. Okay, we're back. I just shut down the little client there. That's the only thing I've done. So let's take a look at the code for this guy. To begin with, we're using our orb, our object request broker, and in this, actually we're not using the orb, we're using the IDL compiler, the interface definition language compiler, and there's another video on that, you can watch it, but basically we're just using it to generate some constants and some enumerations. And if you go look at the other video that I did, there's two, one on how we use it to create really smart enums, which you'll see soon, and how we also use it for as an actual object request broker. But in this case, we're just using it to generate some constants and some enumerations that are shared between the client and the server. So these are the data points, and this is the message type, of which currently there's only one, which is here's some sensor data. We could have others, of course, and these are our values that we receive. All right, so we're going to use that to generate these two files here, the shared files. The IDL compiler generates those. So it's just, we won't look at that, but you can go look at the other video if you want to see how that stuff works. All right, so the basic, let's just go through the simple stuff here. The main Cpp file, all it's really doing is just declaring our singleton. I think we have a concept of a singleton facility object for each executable or DLL, or whatever it would be on the particular platform. So in this case, we're just creating one for this particular program here, and it's our only global data. And then this is just a sort of a magic glue thing. And we're starting the main thread up on this facility object on this main thread method, which we'll see in a minute here. So basically this is just getting us started. So there's no main in a program like this for us. So the main header is fairly simple. It just brings in some underlying stuff. This is our general runtime library stuff. We need sockets, and for the net guy is just for JSON stuff. However you pronounce it, I say JSON, whatever it is. And then we just, if we were to have other CPP files, we would make our facility, our singleton facility object visible to them. In this case, we only have one, so that's kind of a waste of time, but it's a common thing to do. Okay, so now let's look at the facility class itself. Everything is basically in this one class, and that kind of is nice because when you have multiple threads, it means everything's running within the context of a single class or a single object in this case. So it's very easy to share data, etc. And we'll see how that all works. So we implement the underlying facility class, and we also implement this mix-in interface for signal handling. And we override handle signal, and all this is letting us do is just see control break type stuff. So when we this will get called when that happens. We use that to shut ourselves down. This is where we started up the main thread, right? So this is where everything's going to start at. We start up to 4 worker threads, or we start 4 worker threads, so we could have handled 4 sensors. We need a queue to put incoming sockets into. So we have this is a very standard, thing in TCP/IP type servers. You have a listener which listens for connections, that generates a socket. The socket gets given to somebody to process. So our listener will dump. We're going to create a queue of stream sockets. The listener is going to dump sockets into this, and the worker threads are going to grab them out and service that client. And this is how we store our data points. We have one of these for high values, one for low values. So this is a fundamental array which has a element type of int4, and this is the index for it. So we can do indexing on enums, even though they are enum class safe type enums. We don't have to do any conversion or anything. We can directly use them as indices. We have a couple of little helpers to read values from the clients. The protocol is really simple. It sends a magic marker value first, and then it sends the number of payload bytes that are coming. Then it sends a XORed version of the payload bytes for safety, and then it's the payload bytes. So these two help us read out those initial values. Here's our listener thread. We're going to start that here. So all he does is just listen for incoming connections and dump sockets into the socket queue. We start each of our worker threads up on this guy, and this is just a helper at the end to format out the data points. Another helper. This is called for each of the worker threads that gets a connection or that gets a socket. He calls this to service that client, and we just service it until the client goes away. Each time we get a message, we call this. This gets the raw data. He parses the JSON message out and stores the data away. And a couple of other helpers just to avoid grunt work code. Right, and then these are just the values, the members. So this is our low and high values list, our queue of sockets, our worker threads, an output console so we can dump output. This is an event. The main thread just sets everything up, blocks on this, and our signal handler just triggers this event to let the main thread go. We need to protect the console and these guys here. So each thread is potentially outputting messages and updating these lists, and we use this mutex to protect those. This is our socket listener, and we do some columnar formatting at the end of the value, so we need some stream formatters to do that. And this is our listener thread object. Right? So, and this guy here is just a collection of these thread objects. So that's the header there, and let's look at the code. We call our parent facility class. We tell it what our name is. We give it some information. In this case, we're telling it we have a message file, so it'll load that up, and that's here. That just has loadable text information. And then we set up our low and high values. Say this is how many entries in the array, and we set the low ones to the maximum value and the high ones to the minimum value, and that way we know whether we got a value for them. And any incoming value will be lower or higher than these, and will automatically get stored. Right? We create our socket queue, and we tell it we want it to adopt the sockets, and we say it's thread safe. So all the worker threads can block on this, and the listener can dump stuff into it. They don't have to do any explicit synchronization. Our workers, and we tell it we want it to adopt the threads, and we set the initial and the max count. So that's a fixed size guy. Here's our main blocking event. Our socket listener, we tell it to listen on 9999. Normally we'd get that from like a command line or something. And here's our 2 stream formatting guys. And we set up the thread listener. And as before, we're pointing it to a method of this particular class. So we're pointing it at eListener thread. Okay, so here's our signal handler. That's simple. If we get a control C or a break, we just trigger the event queue to let the main thread go. Here's our main thread. We let our calling thread go. That always is done. That lets us get information out of this incoming pointer if we want to before the other thread is let go. This is this thread. And so we add ourselves as a signal handler so that we can get the call above. we install just a logger object. There's a logging framework in some other languages. This would be called something like dependency and injection or something like that. So we're basically just installing a global logger. In this case, it's just a simple local file logger. And most of our stuff we log to our own log server, which is something that's more discussed in the object request broker video. We log a message just to say we're starting up, and then we dump something to the output console to say we're starting up. We initialize the socket listener, and we just tell it which protocol to use. He already knows the port. We set it above. And then basically we go through, and for each of our worker thread count, we add a thread. We give it a unique name based on its index, and we point it at the worker thread method. Then we add it to the worker queue. Then we go back for each of them and just ask them to start. And this is just a callback via Lambda. And then we start the listener thread. So at this point, everybody's up and going. All the initialization is done. So now we just output that we're waiting for client messages, and we block on this queue here, or we block on this event. When the user control sees us out, we say we log some messages and display messages that we're shutting down. We go through and do some non-blocking shutdown requests on the threads. All threads in our system are owned by something, and everyone has to be shut down cleanly. So in this case, what we want to do, since we have a number of them, we don't want to wait for them each in sequence. So we go through and do a non-blocking shutdown request. That starts them all shutting down in parallel. And then we can go back here and we can wait for each of them to die. And there again, these are just done through these for each Lambda-based callbacks. The NC means non-const. There's a good reason for that. I won't get into it now. We can now clean up the socket listener. Since the thread isn't using it anymore, he's shut down. And then for it, just in case there was any sockets left in the socket queue because we just happened to catch it at the right time and a worker thread didn't get around to getting it, we iterate those and we just shut them down cleanly to be polite. We could have just dumped them probably, but I'm trying to be a good boy. And then we can remove them from the, we can flush that queue. He owns them, he adopts them, so he cleans up those sockets. And then at the end, we just display the data here. So we're displaying each of the data points and the low and high values in a columnar fashion that we collected. Okay, catch some errors if they were to happen. So now let's get into the meat of the thing here. So these are our two reading from socket values things. So one of them is called at the beginning, since it's okay for the socket to have been closed at the start, right? That's not an error. So we have this one that is tolerant of the socket having been shut down, and it just returns a true or false to say whether it got something or not. And of course, we have to be careful here. We're assuming that these values are little endian, so if we happen to be on a big endian system, we do have to swap them in this case. And this one is the non-tolerant one. So this is what we call after we've gotten the first value, so everything else has to be there. So these will throw if they don't get their value. And they're just calling a helper that I created in order to avoid having all the grunt work of doing the throw here specifically. This is the listener thread. All it does is it just loops until it's asked to shut down. We actually initialize the socket listener at the startup. In a real program, we would probably have a little state machine here. Because we might not be able to get the port when we start up, so we would have to wait until we can get it. In this case, we just assume it's already gotten because we did it at the start. So all we have to do is listen for connections. So we just call on the socket listener to listen for a socket. And if it gets one, we will get back a pointer to it. We throw it in the list of our collection, our socket queue, and he owns it now. And then we just output a message to the console. And of course, we have to synchronize that. So we use a mutex locker to lock the mutex while we output that. Okay. And then this is just a helper at the end to format the data. We want to display a question if we never got a value and else display the value. So it was kind of messy to do it in place. So I just wrote this little helper here. So for each of the data points, we pass it the low and the high values and he formats that stuff out. And the stream formatter guys set width and justification and all that kind of stuff to make it columnar. Another helper just to throw a system exception that we got a system exception in one of the threads since we have a number of threads and we don't want to do this over and over. Okay, so here's our worker thread, and this is where most of the work is done. So what we do is we wait for a socket to become available by blocking on the socket queue. If we get one, we output a message saying we're servicing that client, and then we call service client with the socket, and we pass our thread object to him He could get it himself, but we already have it, so it's more efficient to just pass it. And then when that returns, we just say we're finished processing this guy and we're done, and we go back to waiting on sockets again. So that's pretty straightforward there. The top level loop, we put the socket into the socket janitor, which ensures that it gets shut down and cleaned up, and no matter how we get out of here. So if we throw, if the servicing throws, we will still clean it up. This is the service client guy. This is where most of the work is done. We need some values to store information. We need a JSON parser to parse the messages. We have a buffer here that we're going to read the raw data into, and then we wrap a text input stream around that. So we're passing that buffer here as the backing data for that input stream. And we tell it don't adopt it because it's a local. It doesn't need to. We could have given it to him. We could have allocated it and given it to him and let him adopt it. The JSON is going to be UTF-8 encoded, so we give him a UTF-8 converter so that he can do the conversion for us as he reads it in the data. Then we loop, and so we wait a little while for data to be ready on the socket. That could also be a shutdown, either one. If that happens, then we first reread our magic marker value. And as I said before, this one is tolerant, so if we don't get anything, we just break out assuming he's down. Else we check that it really is the magic marker, which is one of the constants that we generated from the IDL over there. So that's where that's coming from. If not, we throw. Then we read our payload bytes and our Zorg payload bytes, and we compare those and make sure that they work. So if those are not equal, then we assume something went wrong. It's just a kind of a cheap and relatively lightweight way of making sure, or not making sure, but helping make sure that you don't get some bogus value and try to read that. If that works, then we just issue a read into the data buffer for that many of bytes. This guy can also throw. There's another parameter here that tells it how tolerant it should be. In our case, I told it I use the default, which is don't throw if it doesn't get it all, and I'm checking it myself, so that I can just throw my own error here instead of his. If it works, then we update that data stream up there, that text input stream. We reset its end of stream marker so that we can just reuse it over and over again without having to recreate it. And now we have the raw data. So we call parse message or parse response with the JSON parser, and we pass it that input stream. He'll use that to stream it in. And this is also a Lambda-based callback. So for each of the values in the file, we get the path to it, we get the value, and we get the JSON value type. We're not really using that here, but we could if we wanted to check it. We know all these are going to be strings. So we check the path against constants from the IDL compiler generated stuff. So for each of the things, if it's a message type, we store it as the message type. If it's the sensor name, we store it as the sensor name. The value is the value, and the value name is the value name. Right? So we're just storing away the values we need. I'm being a little lazy here. If this were a real program, I would have cleared those strings up here, and then down here after the parse, I would make sure that they all got a value. We're just assuming they did in this case. And so we got that, and we use the smart enum stuff to translate the message type into the message types enumeration from the IDL compiler stuff. And if that comes out, message types count, that means it wasn't a good value, so we throw. So then we know the message type, and we operate according to that, which, as we said before, there's only one. It's just the sensor data type. And we do the same sort of thing with the data point. We use the smart enum stuff to translate that. And if it's bad, we throw. Otherwise, we know what the data point is. And the sensor value has to be translatable to an int4, so we try that. And if that fails, we throw. And if all that works, we need to store the data. So we lock the mutex. We output a message saying what we got, so which you can see over here. Sensor kitchen set external humidity to 80. So that's being output right there. And then if the current value is lower than the current low for this data point, and note here that we're using the smart enum to index this collection without any sort of data casting or anything like that, or type conversion, then we store that as the new low. If it's bigger than the last high or the current high, we store it as the high, right? And then there's just some throwing helpers to throw some exceptions. And that's it. That's the entire program there. It's not a whole lot of code, actually. How much is that? That's 577 lines, a lot of which are comments. So I don't know, maybe 300-ish lines of actual code. So something along those lines. Not very much. So anyway, that's what, let's say, a typical server type program would look like using our system. I'm guessing it's quite different from what a STL based program would be like. We tend very much towards the practical and the simple, just no more complex than it needs to be, basically. And of course there's none of the namespacey type stuff that happens in the STL either. So we do use namespaces, but not in as aggressive a manner as they do. And of course the IDL stuff makes things so much cleaner. Some of the stuff would be a lot gnarlier if it wasn't for that ability to iterate through enumeration values. And I guess that's something I didn't point out. So here we're doing we're iterating through a loop here using the enumeration, and we can just do a ++ on it because the IDL compiler generates that for us, right? And a lot of other stuff which you can see in the other video about it. So all these things really make for a lot of, it compacts things down quite a bit. And for something like this, of course, we're indexing these lists, and because these types are not convertible anymore, they're a enum class type enums, we can't use the wrong thing to index these guys. We can't use the wrong type. So that becomes a type safe indexing mechanism as well, which is quite nice. And of course, for anything like this where it's being passed as a parameter, since it's a enum class, that can't be done wrong either. So those types of things really help. And actually, I also posted something on Reddit about the process. I mean, this is a large code base, and it previously did not use safe enums, and I converted them all, and it was something of an effort, but it was well worth it. I think it has come out pretty nicely so far. And there's still some things to do. There's other stuff that you're not seeing here, such as ability to do bitmap enums and to OR and them and all that kind of stuff as well, which is very useful. Okay, so that's it. Hopefully I went slow enough that, if you want to really go back and look at it, you can, all the code has been seen at this point. So all you got to do is just go back through the video, and you can stop it at any point and read as you want to. So we've seen everything, and so you can look through the whole program. If you have any questions, just ask. We'll see you in the next video.